Okay, great. So welcome everybody to another one of our IR-SIG webinars. I will be moderating today. My name is Meredith McGregor. I'm an assistant professor at the University of Colorado Boulder, and I'm one of the co-chairs of the IR-SIG. Before we get going today, I just want to read a few instructions for how this will work. Please submit any questions that you have for our speaker through the chat window. You should see that on your screen. Or if not, you can click on chat at the bottom of your Zoom window. I typed these instructions into the chat window already, so you can refer to them later. For last time we had one of these webinars, we had some unfortunate Zoom rating. So we're going to keep things pretty locked down, which means type your questions into the chat window. And then when we get to the end of the talk, Mike Zemkov, the other co-chair, and I will moderate that Q&A session. You can also submit questions that you have for those of us on the IR-SIG Leadership Council through the chat window as well. We'll wait until the very end of the session to answer any questions directed towards the IR-SIG. You can report technical difficulties in the chat window, and this webinar is recorded. So if you would like to refer back to the slides or the talk, you can find that on our webinar webpage, and that is linked to the chat window as well. And that's a great suggestion, an email address for the speaker. We can likely provide that if Thomas is willing, so that you can follow up with questions directly to him as well. And with that, I am excited to introduce our speaker for today, Thomas Nikola, who is currently at Cornell University. Thomas did his graduate work at the Max Planck Institute for Extraterrestrial Physics and the University in Munich, Germany. He spent some time in Australia at the University of New South Wales before moving to Cornell. And today, Thomas is going to be telling us about CCAT-Prime, an overview of the observatory, instruments, and science goals. And with that, Thomas, you can take it away.
Okay, yeah, thanks very much for the invitation and to give me the opportunity to talk about CCAT-Prime. I hope I can give good information. I was struggling a little bit to get all the stuff together, but I think I have enough. So yeah, so this is the picture you see here is basically a photo art with a sort of a model of CCAT-Prime on its final location at Cerro Chacnator. And in the background, you see sort of the Atacama Plateau. Let's see if I can get my slides moving. Okay, yeah, so all the slides and information you see, I've basically shamelessly stolen from other slides that we had from a workshop that was recently held about CCAT-Prime and was hosted by Mike Fick in Waterloo, and it was kind of remote. So I try to get information from all the up-to-date science cases and then put them in here. To start with, just an overview about the CCAT partnership to get a little bit of a perception. So CCAT Observatory Inc. is a incorporation. It's the Cornell University is the lead of the observatory, and the whole CCAT observatory is consistent with Cornell University, a German consortium led by University of Cologne, and the Canadian collaborators, CATC. CATC is the Canadian Atacama Telescope Corporation. It's again a consortium of universities in Canada, led by Waterloo, and you can see here all the universities that are involved in it, and some other partners. We have also some agreement with TAO, the Tokyo Atacama Observatory, and the main reason for this is because we are sharing the road up to the top of Cerro Chacnator, and we also will share power that goes up to the mountain. The project personnel of CCAT-Prime, we have the director Terry Herder in Cornell, project manager Jim Blair in Cornell. So the office of CCAT is in Cornell. We have project engineer Steve Parsley, a deputy project engineer Ronan Higgins, he's in Germany. Mike Nolter, software engineer, he's in Canada. And we have a power consultant, and then we have some people also in Chile Pedro Correa. He's our liaison in Chile. The project scientist of CCAT-Prime is Gordon Stacy in Cornell. And the instruments that we have on CCAT-Prime is basically a German instrument, CHAI. An instrument scientist there is Urs Graf. And the PrimeCam instrument science is the instrument we built here in Cornell is Mike Niemek, and he's also the liaison with the Simons Observatory. By the way, Simons Observatory, they're building basically copies of the CCAT-Prime. And by now, they're actually a little bit ahead of us in Cornell. So CCAT-Prime telescope. The telescope itself has an aperture of about 6 meters. It's a sub-millimeter telescope, so it's optimized for this wavelength regime. And the optical design is, I wouldn't say unusual. Many people are building off-axis telescopes by now, but it's a bit different than others. It's a so-called cross-Dragoni design, and we have made some adjustments and modifications. So we have a coma-corrected cross-Dragoni telescope design. And the feature of this design is that your primary, which is 6 meter diameter, the secondary has also about the same diameter as the primary. So we have basically two 6 meter dishes here. The primary 6 meter and the secondary also 6 meter. It has the advantage of this design that you get a very nice, almost even focal plane. It's very huge, but you also get a very big field of view. The field of view we have with CCAT-Prime is of the order almost 8 degrees. Obviously, the 8 degrees only work out very well if you go to longer wavelengths. To have good strain ratios and so on, at 350, the field of view is basically a little bit reduced. So the best spots are sort of the inner 2.5 degrees of the telescope. The surface RMS that we get with our telescope is better than 11 microns, so that's a very good surface accuracy. And the one reason why we wanted to have such a high accuracy is because we want to actually push the wavelength observations down to almost basically 200 microns. This is possible up at the CCAT site. Given that we want to do observations for CMBs and stuff like this, we want to make sure we don't get emissivities from the telescope in the atmosphere and whatnot. So the telescope itself was made such that we have a very low emissivity, as we try to minimize the gaps between the panels of all the mirrors, and so this reduces the emissivity dramatically. The pointing error of the telescope is quite good. It's better than 1.4 arc seconds. I forgot to put down numbers of the angular resolution we have. It's of the order half arc minute, sorry. In the telescope itself, it will be a survey telescope, so you want to move over big parts of the sky. And so we have very large scanning speeds, up to 0.33 degrees per second. So that's very fast. And that's what we will use at mostly at 350 micron. This scanning speed is this high only in azimuth direction. In elevation, it's about half this speed. The CCAT-Prime site. So you see down here on the lower right side a picture. In the foreground, you have the ALMA array, the ALMA plateau. On the background, you see the Ceres Chaknantor. And we are not quite at the very top of the summit, but we are just a little bit below. And one reason why we didn't go all the way up is because it's very windy up there. So you have some it's not optimal anymore. And the other reason is because Tau has already sort of claimed the very top. So with where we are about 600 meters above the ALMA plateau. On the top right, you see the transmission through the atmosphere that we have. And even at very high frequencies, you see that at the best quartile of the weather conditions, you get very good transmission at 850 microns. So it's very good. So observation at this high frequency will become routine up at this high side. And what's not shown here, unfortunately, this transmission plot does not go to 1.5 terahertz. Even at 1.5 terahertz, you can actually get very good conditions up there. And so even if you go to the sort of the second quarters of the median, so we still have very good transmission. So it's a very good site, and it's actually worth to actually go up this extra 600 meters from the Alma plateau. As you can see here on this one plot, if you make an instrument like the ones we put on CCAT-Prime, and if you would put, if you compare this instrument on CCAT-Prime to the same instrument on a different telescope, you see that we gain a huge amount in mapping speed. So we gain between several tens to almost hundreds times the mapping speed compared to an instrument on other telescope like the LCT, APEX, JCMT, or the LMT. And even compared to the Alma plateau, so we gain significant mapping speed compared to Alma. On the left side, you see a table that shows us again with the telescope, the possible water vapor, wavefront errors of the telescope emissivity, and then the field of view. And what's shown here, one thing is that we have a tremendous field of view, so that helps a lot in the mapping speed. And here I should point out that the field of view shown here is 78 arc minutes. That's just a single prime cam instrument module. So that's not the full instrument, it's only basically a seventh of the instrument. So even if we have done the full instrument, we will gain even even more than compared to other telescopes. Here's a sketch, a SolidWorks model of CCAT-Prime. So you see it's actually quite a beast. This is the primary mirror here. This is the elevation housing at the moment. It's tilted here at the moment. The primary mirror is, that's the primary. The secondary mirror is over here. And then from here, the beam goes over through the elevation axis to the main instrument compartment here. And we have a second instrument compartment down there. To get the lights to the second instrument compartment, we would have to get 4 optics that gets sort of mounted here and then feeds the beam down. Here's again a sketch with some annotations. So we have the traverse down here. It's we basically have all the most of the electronics, computer stuff. This area down here in the middle is for the servo, and on the left side this is the process space where we have compressors and so on. And then instrument spaces down here, the yellow ones, they're actually 2 instrument spaces. One will be used for a guiding telescope that we might use to see how things work out. And the blue one is for our main instrument for a big beast. Some of those plates you see here in this cross, this is so we can actually have access to the mirror. So we would have to tilt the elevation housing by 90 degrees, and then we can walk here and then actually can adjust mirrors and watch the mirrors. And even so, it's a sort of a 6-meter telescope. It's 6 meter doesn't sound big, but if you put this cross-Dragoni design and everything together, it's actually a quite significant mount here. You see a person standing here, and then so this thing will be huge. I mean, if I compare it, for example, to APEX, APEX is 12 meter, and if I stand next to APEX, APEX would probably seem small compared to, not really small, but it's CCAT-Prime is bigger than APEX, basically. Yeah, and once everything is built and ready, it should be up here on serial track number 4. These boxes you have in front here, these are some containers where we can have some storage, and then if we need to do observations for testing at the beginning, we even have some place there we can run the telescope from up here. The telescope itself is fully funded. So we have all the money at hand. It's mostly funded by a private donor we have here at Cornell, but we also have we got some university funds. But in any case, the money is there, and the telescope is actually being built right now. For the PrimeCam instrument, so there will be two instruments, PrimeCam and a German instrument CHAI for the PrimeCam instrument. We also have funding, but it's just for the cryostat and for some closed cycle system. And we got this funding via a university and startup funds from some professors here. We are still seeking to get funds to actually make the instrument modules that would go inside these instruments. And those modules will have the optics and the detector. So this is a significant amount of money, and we don't have this in hand yet. So we have proposals at NSF, and then hopefully we hear some positive news from them very soon. The construction of CCAT-Prime is started, and we also have started constructing the cryostat for PrimeCam. The first light of the telescope is expected to be end of 2021 or start 2022. So it's basically very, very soon. It's kind of scary when you look at those numbers. For the construction, here some pictures of hardware. The person you see here is Steve Parsley, our telescope engineer. And what you see here is the base rings. They are available. And the bottom pictures you see here, they're making some test site in Germany. So we can do a test assembly of the entire system before we ship it out to Chile. This is important because we want to have very good surface accuracies. We want to have very good high speeds with the telescope. And we need to test this before we go to Chile, because once we are in Chile, it will be taken from the port almost directly to the high side. We have a little bit of a site close at 5,000 meters, but it's just for storage. And all the assembly will then happen directly up at 5,600 meters. And at those altitudes, it's really tricky if you have to debug the system. So we set up a system in Germany right now, so we can do a test assembly and check everything out if the surface accuracies are basically within specs. We won't test it down to 11 microns probably, but we will go down to about maybe 15 or so, and we do the final one then once we're in Chile. And so this test facility is built right now, and we hope to we plan to make actually the testing this year, sometimes maybe in August, given the current pandemic. I'm not sure if August is still okay, but maybe it might push to September, but we will still hope to do it this year. So we will have basically a full telescope assembled at this site this year. In this slide here, you see the road construction. This goes out. So here you see all these switchbacks, this dirt road here. This goes up to the summit. At this point here, that's where CCAT-Prime will be. It's a little bit below the summit, and all the way up here, the summit, that's where Tau will be. And so we need to make this road a little bit, we may have to make the road a little bit wider to get all the equipment up. And we need to make sure it's actually not too steep in various spots. And then some of those switchbacks are very, very tight. Our container wouldn't go around it. So the switchbacks will be sort of widened a bit. And we will not go this route here, but we will go from this side to our CCAT-Prime. And then from there, another road goes up. And this is underway. You see here a picture of the road construction that's happening in Chile. I'm not sure if they're working right now because they also shut down, but this was done still a few months ago. The main driver for building this telescope and to have a 6-meter type telescope is listed here on this slide. We have about 6 main science drivers for CCAT-Prime, and those are the probing-based epoch of reionization using redshift C+ line, basically just looking how the universe went from the dark ages to sort of where we have the lights again, and where everything was ionized. The other science goal is tracing the galaxy evolution and galaxy cluster formation using the Sunyaev-Seldovich effect. And so we can see some, even try to get maybe some dynamics of those clusters and then get sort of the large scale structure of the universe by tracing those galaxy clusters. We will also measure CMB foregrounds, so it's to constrain inflation, and also to help other CMB observations, because foregrounds are really tricky and we have to really properly understand and be able to remove those to be better able to actually use these high redshift and CMB observations. We will also do science nearby. We will use, for example, the German instrument CHAI to study the physics of star formation in the Milky Way and nearby galaxies. And we will do this by observing some submillimeter fine structure lines and CO transition lines and get the dynamics of the gas. Then we also try to probe the galaxy evolution from the first billion years to cosmic noon, basically from the beginning of the assembly to basically where the star formation rate of peaks at redshifts 1 to 3. We try to probe how the galaxy evolves since then. And then we try to also improve constraints on new particle species by observation of the Rayleigh scattering. So that's a very tough one, but the predictions are reasonably well, so it seems that we might be able to see something, or at least get a good higher limit, upper limit, which will be very helpful for other people for the next time. To actually do all those science goals and use CCAT-Prime the way we want it, we have two main instruments. One is PrimeCam, and the other one is CHAI. PrimeCam is a direct detection instrument. It's a modular instrument. It has various camera modules and two spectrometer modules, and its viewing field of view is about 8 degrees. And the second instrument we will have, there is CHAI. It's a heterodyne spectrometer, and it has this high spectral resolution that would be required to do some of the Milky Way and nearby galaxy studies. So let's go first to PrimeCam. As I said, it's a modular instrument. It has 7 modules. On the right, you see basically that's the whole cryostat. It's about 1.8 meter in diameter and about 2.5 meter long. So we have 7 modules. We have 5 camera modules, and here you see the center of the broadband is 220 gigahertz, and we go up to 850 gigahertz, and then we have 2 spectrometer modules. Each of those modules is independent, and we will probably not have all of them for first light. So we try to get enough funding, so we have at least 2 for first light. The field of view of each of those modules is of the order 1.3 degrees. And that's how we get also our full field of view on the sky. Here's a cut through PrimeCam, and here you see actually the modular parts of the instrument. The light comes in from telescope here, and then we have various silicon lenses, a Leo stop here, another silicon lens, and then we focus the light to our detector array that's down here. And then on the back, we have some of the cooling stuff, and then wire harnesses, they go out to the real electronics, which is shown here. It will use a dilution refrigerator, and it will use at least 2 other pulse tube cooling systems to cool down the instrument, because it's a huge beast. And we have to make sure not only that we get everything cold the way we want it, but also to have at least a decent cooling time. Detectors will be cooled down to about 100 millikelvin or so. And the front, we have a small pulse tube in the front, because that's when most of the heat load will sort of dissipate. So we have a pulse tube here that it's a single stage, and it will keep the front at 80 Kelvin. The optics, all the modules in PrimeCam are very similar, and so is the optics. The only difference basically is if you have the off-axis modules, you have to do a slight modifications, because the beam comes in a little bit, it's tilted. It's not necessarily telecentric at the input. And the other difference is because some modules are cameras and the other ones are spectrometers. So that requires a slight change. This is what you see here is the optical design of the spectrometer module, and we use a Phi Pro in here, which requires a very a decent or very good sort of collimated beam passing through the Phi Pro, and that's not required for the cameras, for example. So the cameras can don't need this very collimated beam here. So they have 2 fewer silicon lenses that we have in the spectrometer. But the overall length is about the same for each of the modules. The lenses we use, as I already said, these are silicon lenses, and they will be will have an AR coating. We basically either cut grooves, or we will sort of it's mostly cutting grooves in those lenses to make sure we have a good AR coating for those. The detectors for PrimeCam, those will be large format MKit detectors, and they will be from NIST. And NIST, our collaborators are Hubmeier and Wheeler. And given it's we don't have a full budget or yet for these modules, we're planning to use spin-offs of the blasting and Toltec detectors. The detectors will be also feed-horn coupled. What you see down here is this is a sketch of a mechanical design for a single array mount, and at each module will then have 3 of those mounts sort of butted together. So you have 3 of those here, and then each module will have an array that looks similar to this one. For the readout electronics, at the moment, again, lack of funding. For this part, we have a Roach 2 in the lab, and we also recently got one Xilinx RF SoC for testing. So we're playing around with those. And for first light, we most likely will have a Roach 2 system for the readout. This severely limits actually how many detectors we would be able to read out. With these Roach 2s, we would not be able to read out the full PrimeCam. I mean, in principle, you can do it, but you need so many of those Roach 2s and the power dissipation would be way too much of those. And also the space required to actually just store them would be too much. But for a first light camera or spectrometer, they would be okay. With those, you can only read out about 500 to 1,000 detectors. For the long run, we're sort of planning to use a Xilinx RF SoC for PrimeCam. And so with those ones, you can read, with a single one of those, you can read out about 5,000 detectors. You see an RF SoC on the left side here. That's the one that we have in our lab. And on the right side, you see a Roach 2 that we have in our lab. The other good thing about this RFOC is they need much less power, so the power consumption goes way down. And the power consumption actually is very important for CCAT-Prime, because if the consumption is too high, if you have too much power dissipation, heat dissipation inside the telescope structure, this will affect our surface accuracy and the pointing and the performance of the telescope. So we have to make sure we stay within our power requirements and don't go overboard. This says that it would have a big effect. The a summary sort of the PrimeCam detectors. On the right side, you see sort of a sketch if you have 7 tubes, and you see these contour lines. These are strain ratios, so you see where you have the good spots. So not everywhere you have a good strain ratio. That's one reason why we want to have the highest frequency module in the center, and so the lower frequencies one around. And so this is at the moment still a sketch. The orientation is at the moment just the way it happened to be for making this sketch, but it's not necessarily the final orientation. For the camera modules, for the 220 gigahertz module, we will have about 8,000 detectors, and so it goes up with the higher frequency to 21,000 detectors for each of the 350, 410, and 850 gigahertz. The spectrometer module, there's 2 modules, and they will have a 250 and 360 gigahertz, and they will have about 10,000 and 21,000 detectors. The spectrometer module actually is kind of a nice feature. We use a 5 per interferometer in there to get the spectral resolution we need, and we call this, given that that's the main instrument for observing the epoch of ionization, we call it also the EOR spectrometer module. The resolution we will have here, the spectral resolution is of the order 100, which is pretty good for doing these EOR observations. And what happens if you have a Fire Pro, you basically have you get sort of a resonance. The Fire Pro makes a resonance cavity, and multiple integers of the wavelengths that fit the separation of these mirrors of the Fire Pro will make it through. And at this resolution we have, there are actually two frequencies that will make it through our Fire Pro at this resolution here. And what we do is at our detector array for the spectrometer module, we actually have it set up so one of them has the higher frequency, while the other two are the lower frequency detectors. And what we do, we put bandpass filters on top of them. So a single spectrometer module can actually or will actually observe two lines simultaneously, or two frequency ranges, lower frequency ranges simultaneously. What you see in this plot, so the blue one is the atmospheric transmission that we have up there, and then the orange plot here and the blue and the green, what you see here are bandpass filters that will be put right in our detector array. The other thing that happens is actually, given that many of the off-axis beam come in an angle through the Fire Pro, there is a small shift in the frequency that actually makes it through the Fire Pro. It means if you go off axis or off the center of this spectrometer module, you actually have a slight shift in the frequency. And while sometimes in the past this was usually a disadvantage in most instruments, but we actually use it as our advantage. In our case, what we do is we can actually, when we do our full survey maps on the sky, we not only observe a single frequency, but we will make an observing strategy so we can get actually a much bigger wavelength coverage over a specific map. So we use this shift in frequency, if you go off axis, as our advantage. Here is a big list. This slide, the next slide, is a list of sensitivities we have for PrimeCam. And in this list, it's set up for what kind of service you want to do. Like for the epoch configuration survey, then we have the dusty star formation galaxy survey, and then we have the Sunyaev-Zel'dovich and CMB surveys. These are the fields that we want to cover with those surveys. And then these are the areas that will be covered. You see, for example, we have a 20,000 square degree coverage for the CMB observations, and we will spend nearly 4,000 hours to to cover this region. If you observe over this full region at this time, you get about 11 microkelvin per arc minute square at 270 gigahertz. And for the dusty star formation galaxy science driver, we get a confusion limit of about 2.5 millijansky per beam at 860 gigahertz. And here, at the end, what you see here, there are other surveys people have done with various telescopes and instruments. And so you have a big wavelength coverage. So they're listed down here. So each of those fields has additional supporting surveys. In this sensitivity table, this is set up mostly for the top ones, mostly for the more or less for the CMB community, because they use what for me is a little bit hard to grasp is they have their CMB temperature units. So you have microkelvins for the entities and so on. So that's what this is. And so you have these various cameras, these modules for those frequencies. You see what kind of noise equivalent temperatures you would get. And this is for 15,000 square degrees in 4,000 hours. And then we have these smaller fields. These are then more for the EOR part. And so they have a few hundred square degrees and less hours. And this here at the back is the same for the spectrometer. The spectrometer, given that it's done EOR, those fields are a little bit smaller, but we can spend lots of hours in those fields. The other instrument that will be on CCAT-Prime is the CHI instrument. This is built by the Germans, by mainly University of Cologne. And this is from the slides from Urs Graf that he had a few weeks ago. So you see a spot by a SolidWorks model here on the right. Chai has two systems or two instruments, a low frequency and a high frequency system, and they observe simultaneously. The frequency range they cover is between 450 and 500 for low frequency, at 800 to 820 gigahertz at the high frequency. Noise temperature is pretty low, and they have a large IF band, and so they get a good velocity coverage, and the resolution in gigahertz. Okay, I missed something here. That's the kilohertz resolution, not kilometers per second. It's 2,500 and 1,500. The beam size in Chai is 26 arc seconds for the low frequency and 15 arc seconds for the high frequency. And this HETRA instrument is not a single beam, but it's actually an array of heterodyne array. So with all those, it's an 8x8 pixel array, so to speak, and its field of view is 7.5 arc minutes by 7.5 arc minutes for low frequency and 4.5 by 4.5 for the high frequency. And here's a picture on you have the footprint of Chai overlaid on a Sophia picture taken in C+ of the Horsehead Nebula. And the other nice thing of observing with Chai on CCAT-Prime is because the angular resolution for these high frequencies is very similar to the Sophia resolution you have in the terahertz for C+ and O1, so you can make very good comparisons. The Chai instrument will mainly focus on those lines, the CO43 and the carbon fine structure line, and the CO76 and the other carbon fine structure line. So those windows will be in their first light instrument. So they will try to get a broader coverage of this window on later on, and also to get system coverage that goes to the very high frequencies, that they can actually observe high JCO lines, or even get to the nitrogen 2 205 micron line. The way CCAT-Prime will observe, given the science goals we have, and these are basically require all large fields on the sky. So the CCAT-Prime will not be a telescope where you can submit, say, I want to observe this galaxy, I want to observe that galaxy. It's basically, there will be observing campaigns. Each science driver will have its campaign that will probably last a month or so, and they will then cover big parts of the sky, and the observing strategy is then optimized for the frequency they're most interested in. This does not mean that the other instrument models will not see anything. We will always use all the instrument models that we have available. So even the ones that might not be necessary for the specific science driver, but you can use this information for other science drivers. So what you see here is some of these areas we want to cover. So these green boxes here, these are some of these areas we want to get, and those are also part of what ACT is doing at Atacama. So these are one of the main parts, the big ones for the CMB observations, and also on this side. And then we have some smaller fields that will be mostly covered, most important then for the dusty star formation part and for the EOR. So these are the smaller regions here. These are basically some gamma fields. You have the Cosmos field will be covered. Then we have the stripe 82, and we also will get the CDF down here. Yeah, as I said, we recently had our science workshop in for CCAT-Prime, and here's again a list of all the science working groups we have. We have the tracing epoch of ionization, and then also the coordinators who are sort of the leaders of these science groups here. It's Gordon Stacy and Dominic Riechers from Galaxy Clusters, Nick Battaglia and Kaustuf Basu, and then we have tracing star formation, Scott Chapman, and we have Mike Niemek for the CMB, Dan Merbuk for the Rayleigh genes. And we not only do the ones that have a very beginning, but we also have these kind of, I wouldn't call them necessarily niche observations, but these are things that can actually, some of the data we do when we do our maps, they can be used actually to do time domain astrophysics. Given that we cover many of those areas in a certain cadence, we will still have to figure out exactly what we will have or what kind of cadence we will have. But we cover those regions, the same region over and over again. So there will be ways to actually use this data to see time domain effects like outbursts of young stellar objects and stuff like this. And also given that we have I forgot to mention at the prime cam part, all the camera detectors and these camera modules have polarimetry capability. So we can get polarization observations, and so they can be used to study magnetic fields and to some other galactic science. So I now go quickly a bit over some of the science part, and now the next few slides, I'm a little bit weak on those because this was the last few slides that I sort of managed to get before my time was over. So first I go into the ones about the observing the epoch of reionization. What you see here in this picture, you have basically it's a slice through time. The Big Bang is on the left side, and we are basically on the right side here. You have at this part here, you have the recombination at about 370,000 years after the Big Bang, or 300,000 years after the Big Bang. That's sort of the surface of last scattering. That's where we basically get the CMB observation, and we want to do some science with them. And then after this, you have those dark ages where the universe was neutral and not much was happening. And then only at the end of the epoch of the dark ages, you basically get the first stars and galaxies which start to ionize the universe again, and then you end up making those galaxies, and then later on all the universe is ionized. The range of the epoch of reionization is basically from here to here, from the start to the end. This is the redshift range here is still not quite set, but it's depending what papers you read, it can start from the end of reionization about redshifts of six-ish or so, and the beginning can be up to redshift of 15 or 30, depends which papers you have. The science goal of this is basically determining the topology and the time scale of the cosmic reionization. So we want to see how long does it take and how actually how those ionizing bubbles sort of start expanding and where they show up and if they make build kind of structures. And to do these observations, we will use the C+ fine structure line. It's which is at redshift, the rest wavelength of C+ is 158 microns, and we will observe this line at redshifts 3.5 to 8. And this line is a major tracer of star formation. It's one of the strongest lines you actually get from galaxies in total if you observe galaxies. And it's a very good tracer of star formation. And when we do these observations at these high redshifts, what we see actually aggregates of the emission of these star-forming galaxies. So we don't necessarily solve individual galaxies. We have various galaxies in the beam, but we basically see those these star formation, and so then therefore the ionization bubbles to grow when we observe these kind of fields. And then by tracing this this C+ over this time, we then see also the evolution of those of these ionizing air volumes, and so we can also then we then follow the galaxy evolution formation, so we can then trace how this works out too. Here's a picture. When we do these observations, what we do, this is the Phi Pro observation basically. We basically set the Phi Pro at a specific frequency and then observe a slice in the universe. So it's basically what we get is basically a 3D cube, two dimensional, and this third one is the spectral, or then the depth. And when we slice this up, you basically get this fingerprint for each redshift that tells you what kind of power spectrum, how big some of those emissions are, and then if you have voids in between and stuff like this, and how far apart they are from each other and how strong these are. And so there are different, we have an early baseline of full science cases, and those just depend on how many of our instrument modules we have available. If we have the full is basically if PrimeCam is fully populated with all 7 instrument modules, and the earlier one, it's when we might only have 1 or 2 modules to do the science. And so on the right, what you see here is then a prediction whether we can actually, if CCAT-Prime can actually see this signature of the C plus from those galaxy aggregate emission. The solid lines you have here, these are models what people expect to have, what kind of structure you will see at different what the power spectrum would be of the C plus emission for different kind of structures you have. And that's structure is a K vector, is per megaparsec. So bigger structures are on the left, smaller structures are on the right. And depending, there are various models here. One is from Chung et al, and it's this plot is from his paper. And then there are other models of what we would expect. So when you see the PrimeCam sensitivities are in the is the left the dotted ones, the red one, and let's see, it's okay. I guess I got wrong. I guess I have not the plot I thought I would have. Anyway, you see the CCAT-Prime or PrimeCam sensitivities, we are usually well below what people would expect. So we have enough sensitivity to actually see all these structures. The others that are shown here is the sensitivity estimates for, this is for concerto, and the other one is for time. These are also C plus intensity mapping experiments. So, and CCAT-Prime is most of the time is way sort of below of them. Only here the high redshift of 7.4, and it's small structures. So we we lose a little bit here. For these EUR observations, so the EUR is not a sort of a point in time. The reionization happens over a huge, or not a huge, but over a specific time scale over range, and that's because the the reionization depends on the free mean path of the ionizing photons that travel through the intergalactic medium. And basically, it depends how far they can travel. It depends based on the density structure of the IgM. So for overdense regions where they cannot travel that far, so you have sort of these regions ionize first. You should see the first ionizing bubbles in those overdense regions. And so then when you have those galaxies and the galaxies start clustering, so they will then drive the evolution. So that's where you will see sort of the ionizing bubbles to grow. On the right side is this sketch. What it shows here is if you plot the power spectrum of the C plus observations versus the scale, and you see that it's small spatial scales. What you see is basically kind of a shot noise. Something that looks like shot noise in your power spectrum. This is due to basically the galaxies that are in there, because these are small scales. On the larger scales here, the large scale structure, this is where then this is the C plus power spectrum is then dominated by the clustering of the galaxies. And by the way, PrimeCam and CCAT-Prime, we will not only observe the C plus, we will have various other lines that also will show up. For example, the 0388 micron lines will show up, and it's a strong line. And we also will get some CO foreground contamination we will take out over time. And it was pointed out in the workshop we recently had that it's kind of funny if we go to very high redshift and want to observe ionizing bubbles using the O3 lines, actually our C plus intensity map is kind of a foreground we have to remove in order to see actually the 88 micron line. The other science, one of the other science topics we want to cover is observing or tracing probing the galaxy and galaxy cluster formation. And for this, we are going to use the Sunyaev-Seldovich effect. On the left side, you see this very nice sketch from, I cannot pronounce his name. Its first name is Tony. I guess many people probably know him. So you have a sort of a galaxy cluster here. You have the hot plasma of the galaxy cluster. You have a CMB photon going in there. It hits a free electron, and then it gets basically you have a cold photon coming in here, and you basically get a hot photon towards you. That means basically, given the CMB is a Planck, basically a nice thermal emission, you basically take photons out from the cold part of this function and put them into the hot part. So this distorts your Planck curve. And this distortion of the Planck curve you can measure. If you compare the distortion for different wavelengths, what you see then here on the right, you get this very special profile here for different frequencies. You see at low frequencies, you take basically photons out of the Planck curve and you put them into the high frequency one. So the black curve here is the thermal SC effect, but you have also other SC effects that play a role when you do these observations. And one, for example, is the kinetic SC effect, and that's because those clusters are not sort of fixed. Those clusters, they are moving, and because of this motion, you actually you get another distortion of your black body, and you get this as higher order effects. So this red curve here is actually amplified by a factor of 10 to make it visible. Otherwise, it would be very close down here. And the other thing you will find, you get a relativistic Sunyaev-Seldovich effect, and that is due to the temperature of the free electrons you have here. And so it depends when you see this. If you get very high temperatures, those electrons move around relativistically. So you have to take relativistic effects into account when you make these kind of plots. And this will then show up here. The bands that you see here in these plots, all the colored ones, will be the bands that we will have for PrimeCam. The gray ones on the left, these are bands that are covered by Advanced ACT-Pole and Simons Observatory. And the ones you have here on the right, these are basically PrimeCam. I mean, you see on the bottom, this long part, that Advanced ACT-Pole and SO, they also go to a little bit to higher frequency, but they do not cover the full profile of the SC effect. And so those people, the people from ACT-Pole and SO, to take full advantage of the using the Sunyaev-Seldovich effect, they will also need PrimeCam to help them out a bit. And that's also especially important because what you see here in the green curve is dust still plays a big role in the whole system. And the dust will have a significant effect in your observation, and you need to be able to account for the dust. And you can only do this if you have higher frequency coverage of your observations. And that's what PrimeCam will and CCAT-Prime will provide. Another science topic then is I want to go is tracing dusty star formation over cosmic time. This is basically the one of the big science topics we have for CCAT. And what people have found out over the last few decades is that about half of total energy radiated from galaxies is basically emitted in the infrared background, the cosmic infrared background. In this plot here, what you see, you have basically on the left, the blue one is sort of stellar emission, and a lot of the stellar emission gets absorbed by dust and re-radiated by dust, which is then you basically convert a lot of the radiation, the energy from the optical into infrared emission. And the half of the energy that actually is coming out of the CIV. However, at the moment, while we know that a lot of energy comes out there, we have not found all the sources that actually emit the CIB. We can only see the overall emission, but we cannot really resolve the emissions, so we don't know exactly what type of galaxies are actually contributing to the CIB. And up to now, it's wavelengths longer than 250 micron, which is basically everything to the right of here. Only 15% of the CIB has been resolved into individual galaxies. So there's a big chunk that's missing in our picture. And to get a better handle on those galaxies, with CCAT-Prime, what we can do is we can we get our 350 micron module, and we can go very deep, and we have a much better resolution than Herschel, so we can try to resolve the CIB at those wavelengths. On the right, what you see here, the top image is a Herschel confusion limited image. You have a white stretch here, is 10 arc minutes, and on the bottom you see what we would expect for the CCAT-Prime confusion limit. So you see we see many more sources than what Herschel could have seen, or that Herschel saw. So we try to be able to help improve the find out what galaxies and what contributes to the CIB. And with CCAT-Prime, we hope to be able to resolve up to 40% of the CIB at 350 micron. So our confusion limit is about 2.5 millijanskis at 350 micron. So we try to get a better constraints on the bright and also on the luminosity function of the galaxies, and sort of see how the environment on galaxies are impacted. On the lower left side, what you see here is a plot of various surveys, and it's of what kind of error they have covered and how deep they went to the confusion limit. And you see most of those surveys are sort of on the kind of a diagonal, it turns out here. And what CCAT-Prime will do is the service that we sort of envision at the moment is this red X that we have here. So we cover sort of this real estate down here. So we have a very big area, but we also can go to a very low confusion limit. People have pointed out that it might be worth to not necessarily go to make a big field and to go shallow, but we might try to envision another little survey where we don't cover such a big range, but only a few degrees square, but basically go much deeper, sort of what people now talking about super confusion. And hopefully we can study some other new exotic galaxies might show up if we do these very deep observations. So we can still sort of revise or refine some of our survey strategies, and then see if we can somehow get sort of fields that are small but very deep that we can do and observe, and then see what we get from those. The science driver for the galactic system, for the nearby ones, it's the science driver basically is for CHI. There we go for trying to actually study the galactic ecosystem, which is basically trying to figure out how the interstellar medium, the ISM, how this actually is distributed, and where the stars are forming, and how the stars are affecting the system, how the molecular clouds are being formed nearby, and all this kind of cycling of stars in ISM. And to do this, we want to try to resolve structures within clouds. Basically, we want to go to observe filaments, and that's also a very hot topic for other observatories to get to these kind of levels. And with CHI, with this very high spectral resolution, we not only can get the sort of spatial resolution of some of those filaments, but we can also get the dynamics. And this is important to figure out and see how turbulence and mass flow affect the entire system, how this affects the cycling of the ISM and stars. And so CHI, the main lines I mentioned before, are the CO4-3 and the 7-6 transitions, the rotational transitions, and both of the C1 fine structure line observations. On the right, what you see here is a synthetic map, a simulation, And what we will then try to do with CHI is we will try to compare these CHI observations with those synthetic maps and see if some of these CO, what this, for example, for Sophia, and this might be appropriate for CCAT, how these line profiles, what we can learn from them, what and how they are, these line profiles, what they can tell us about turbulence and so on. And to see those, actually the mid-JCO lines and the C1 lines are very important to observe. Especially C1 would be important because given the filaments and how optically thick they are, you might not necessarily see CO in all of them, but you might still see C1 in many of those. And then there was but it was running out of time to prepare more science driver slides, and so I'm just listing here at the end what else we want to do. And one is on the very top here is actually measuring the CMB foregrounds to constrain inflation, and that's a very important topic. And so this is done a lot by also Mike Niemek here in Cornell, but also by the group in Bonn with Kaustof Basso and his team. They are trying to make very sophisticated models and what we should expect when we do these foreground removals. And for those observations, we will use the polarimetry capability of CCAT-Prime to do polarimetry observations and then get detected dust and remove dust foregrounds and so on. And last but not least, here what I have is the improving constraints on new particle species. This is being done by observation of the Rayleigh scattering, and there I don't feel confident to actually go into detail. It's way above my what I've learned so far. But it's so you always see Rayleigh scattering when you observe the CMB. The tricky is actually to extract the signature of the Rayleigh scattering because it's a very small signature you have, and it's not necessarily clear if we can get um, if we can detect it, but we will definitely see a very good upper limit. So we are really pushing down. We would get the best upper limit that would be available at the moment for those Rayleigh scattering observations. And now at the end, just a summary. So the one thing, hopefully, you should take off from this talk is that CCAT-Prime is under construction right now. It's actually underway. So because often I hear people saying they thought CCAT-Prime is dead or nothing is happening, but no, CCAT-Prime is the construction is underway, and we are there's no showstopper anywhere. We have our trial and test assembly this year, and hopefully things work out fine. So we will get stuff to Chile next year, and hopefully have first lights end of 2021 or start of 2022. The instrument to actually populate PrimeCam and do observations PrimeCam. So the cryostat is in fabrication. We actually have a company that is building the cryostat right now, and we are now trying to get more funding to actually make the detectors, so we don't have to go through our labs and sort of scavenge some Xilinx or Roach tools that we have still for testing there, and then make our first instrument using this, those sort of leftovers, but we can actually make the full full module and get the optics. And we do have the silicon. We have still to actually make the lenses out of silicon, but so the silicon itself we have also in hand. And the one thing I have not mentioned, we actually together with the PrimeCam, together with this 7-module instrument, we are actually building a small version of it, a single module instrument, because this would be much easier to handle, and it might be much faster to actually set it up for a first light camera. So that we have a single module instrument, and there this single module instrument, the company is also constructing the cryostat for it right now. And the other thing that I forgot, I now realized to mention, is the Canadians. They are developing a 350 micron module for a first light camera, and they make one using HDPE instead of silicon, because they try one of their goals is to have some 350 module very quickly and not too expensive. So we have something we can fully test the telescope for its performance, because you can only test the best performance telescope if you go to the highest frequency. So we would need the 350 micron camera module to make the ultimate test of CCAT Prime. And then all these science teams are working to refine the observing strategies and sort of to get the optimal science return from CCAT Prime. And that's all I have. Thanks very much.
Great. Thanks, Thomas, for a really wonderful talk. So we're at the top of the hour, but I still want to open it up for a question and answer session. If people have questions outstanding, you can either type those into the chat window and I will moderate that, or if you're familiar with using the raise hand function, we can try and do a raise hand through the participant window as well. And while we're waiting for people to kind of get their thoughts together, I just wanted to thank everyone for joining us today. As a reminder, we have these talks once a month. So usually the first Tuesday of every month at the same time, 1 p.m. Eastern. So the next one I think will be June 2nd. And if you are interested in speaking at a future webinar, or you want to nominate someone or suggest a speaker, please contact any of us on the Leadership Council with your suggestion. We especially invite suggestions for earlier career scientists from diverse backgrounds. But thanks again for everybody for joining us, and please feel free to type questions into the chat window or raise your hand. We'll hang on for a little bit. And I know, Thomas, there was a request for an email address for the speaker. So if you feel comfortable providing that, I'll let you type that into the chat window yourself.
Okay, let's see if I get there. Okay.
Great. Perfect. Okay.
Yeah, I see one question about from Jens Kaufmann. How does CCAT Prime compare in size with the ALMA antenna? So an ALMA antenna has a dish of an ALMA antenna is 12 meter, and we are 6 meter. ALMA is an interferometer, so their primary beam is slightly, well, it's basically the diffraction limit of the telescope is the primary, and then given that the interferometer, they get this very high angular resolution. With CCAT Prime, we have a smaller dish, and so if you would go, for example, for a point source sensitivity, just if you have a very compact source, I mean, ALMA would win. There's no question about it. If you go for observations where you have where you're interested in surface brightness as something that's extended, an instrument or a telescope like CCAT Prime will win over ALMA, because ALMA will miss a lot of the extended emission. And also many of the science cases we have, they require making huge maps. And to make huge maps, what you need is a telescope that has the surface sensitivity required, and that you can have a significant mapping speed. So you want to cover a big part of the sky many, many times to go to a certain sensitivity depth. And with ALMA, you cannot do this, because you have this very tiny field, and just to move all the antennas over basically thousands of square degrees would require, well, I guess the next few decades of ALMA just for a single survey.
Great. So we'll hang on for,
yeah.
Go ahead, sorry.
Yeah, so for some of the observation, especially some of the dusty star-forming galaxies part, where we try to trace them over the history of the universe, especially from the very beginning to the cosmic noon, if we find some strange exotic galaxies or objects, I mean, there you want to follow up with ALMA. I mean, CCAT Prime can only find them. to get the details of what these beasts are, we need then other instruments, other telescopes, and ALMA would be a very good instrument or telescope to actually look or get more information about those sources once we find them.
Yeah. Al Wooten put into the chat window that a significant step toward the Atacama Large Aperture Submillimeter Telescope is now a subject of a European study.
Yes, yeah, this I think they call it ATLAST, and it's a telescope that's bigger than 30 meter in diameter. And I mean, I'm not sure if how many people know the history of CCAT or CCAT-Prime. The whole project started by now more than 20 years ago, and at the very beginning it was I think it was a 25 or 20 meter mid-infrared telescope to a millimeter, and it was way too expensive. Then it became a 25 meter submillimeter telescope, and it was actually mentioned at this time in the decadal review in 2010. But unfortunately, for whatever reason, we never got funding through the NSF, even we have various approaches. So it shrank and shrank and shrank, and that also changed a little bit of the science drivers we had for the telescope. But we had many of our faculties here, they actually have this science driver now for 6 meter type telescope. And for the EOR, a 6 meter type telescope is basically optimal because the angular resolution is sort of the size you expect for those galaxy assemblies where you get most of the bang for the buck. So the size actually is pretty optimal for the science we want to do. And at the CCAT-Prime sites, CCAT, the whole area that we have is a little bit bigger than what will be fenced in right now. And CCAT-Prime is not necessarily put in the middle of our area, but a little bit to the side. And we try to keep space for future bigger telescopes up there. So a bigger telescope is not out of the mind yet. And yeah, the European, the ATLAS telescope, maybe there's a chance in the next several years, 10 years, 5, 10, whatever, how many years, to get a big telescope next to CCAT-Prime.
Great. So if anybody has any additional questions, please feel free to ask them. Otherwise, I think we'll end it here and say thanks to everybody for joining us and hope to see you online again in June for another one of these talks. And thanks to Thomas for a really wonderful talk today.
Yeah, thanks for everybody for attending.